Welcome. Today we'll be considering question 2, which has 3 parts, which read as follows. Show that the power set P of a set A is an abelian group where the group operation is the symmetric difference A symmetric difference B of sets. 2 is what is the order of this group. And then 3 is write out the multiplication table for this group in the special case that the cardinality of A is equal to 2. Let's start with part 1. Actually, first let's give you some time to work on it. Then we'll do some hints. Then we'll start with the proofs for part 1, 2, and 3. Alrighty then, for some hints, let's try to remember some alternative ways of writing the symmetric difference that perhaps will show more easily that we have an abelian group. Next, we'll check the order of it by recalling what the definition of an order of a group is as opposed to the order of an element. And finally, we'll write out the multiplication table, and perhaps it'll be useful to write out the elements of A as 0 and 1 separately. Fantastic. Let's proceed. So for part 1, I want to show that the power set of set A is an abelian group where the group operation is a symmetric difference. So let's start with perhaps the highest structural element but the easiest to prove, namely that A symmetric difference B is equal to B symmetric difference A. And this comes from the fact that you can think about A symmetric difference B as A union B subtracting B intersect A. And we'll note we've shown before that this is symmetric in the sense that union is symmetric. Union is abelian in the sense that A union B is the same as B union A. So we simply flip this into B union A, subtracting out, this should be A intersect B. So we keep the ordering correct. So this is A union B, subtracting A intersect B. And for this one, we have B union A, subtracting out B intersect A. And these are the same sets since A union B is the same as B union A, and A intersect B is the same as B intersect A. So we see that this is the same as the definition of this. So we have equality. So some other things we need to prove that we have a group. We should prove that we respect closure under the symmetric difference. So the way we show that is by saying the power set is the set of all subsets of A. So the symmetric difference is going to give us a new set, namely A union B subtracted A intersect B, which is still going to only have elements of A, noting that A is this set A. This can only have elements in A. So since the power set is the set of all subsets of A, whatever we get from taking the symmetric difference of subsets is still going to be a subset. So we have closure under that. And then we'll check our other definitions for a group, but they're relatively obvious. Namely, that we need to show that there's an identity, and that identity is going to be, in this case, the symmetric difference of, as we showed in the last P set, in a question a while ago, is we know that A symmetric difference, the empty set, is going to give you A. Therefore, and then we also see that by the abelianness that we just proved, that the empty set symmetric difference A is still going to be A. So this can act as our identity element in here. And finally, we show that there's an inverse law. Namely, we have that we need to show that there is a particular set such that A symmetric difference, that set will give you the empty set, but that's just going to be a set itself. Namely, we see that A symmetric difference A can be A union A, which is A, subtracted with A intersect A, which is A. So A subtract A is equal to the empty set. And that's our identity element. So we have a inverse law in the sense that any element is its own inverse. Perfect. Now that we've shown that it's a group, we're going to try some other things. Namely, when we're asked what is the order of this group, we need to say that we are considering the power set of A with a group operation on it. So the group is over the set of the power set, and the order of a group is a cardinality of the set that underlies it. So this can be the cardinality of the power set of A, which we've shown before to be 2 to the cardinality of A. And so we have the order of the group being 2 to the set A. If instead we consider the order of an element in the group, we see that this is the minimal number such that such that elements return to the identity element. We see that the order of the group in that sense is just 2, because any element, if you square it, if you multiply it by itself, or in this case take the symmetric difference with respect to itself, will always give you the empty set. So we have the order of this group being 2 in that sense. I will note that sometimes we can use 2 to the power set up to the cardinality of A as like an upper bound on this, in that there's no way for a set to have a order of a particular element be greater than that, because that means that as you multiply that to that element, a particular element to itself, it can only go through every element once at most, which is 2 to the cardinality of A numbers. So this will operate as an upper bound if you consider the order of the group as the cardinality of the underlying set. But if you consider it as the order of any element, in this case that's just going to be 2. Finally, we're going to write out the multiplication table for this. So we'll note that by our previous result, this should have 4 elements in it, because the group has, the cardinality of the group is 4 elements. Since we have the cardinality of A is 2, then we have 2 to the 2 is 4. So we're going to write out a 4-column table. And we see that these are going to make going to be quite easy. The first is the empty set, so that's a subset of any set. Here we have the empty set and our element 0. We're going to have the empty set and our element 1. And we're going to have the elements 0 and 1. And this is the power set of A. Now we're going to try that again. Empty set, comma 0, empty set, comma 1, and then 0, comma 1. And now let's write out the full multiplication table, or sometimes known as a Keeley table. Empty set, symmetric difference to empty set, is the empty set union the empty set. Subtracting the empty set is going to be the empty set, and this makes sense because we have the empty set being our identity element in this group. And we'll see that for any element. I'm going to get back that empty set since the any element union itself is going to be itself, subtracted it intersect itself, which is just going to be itself, so anything minus itself is going to be the empty set. Next, let's try this one. Let's fill out this row, and since this identity element, as we've shown before, this is going to simply be all of the groups themselves, or I'm sorry, all of these subsets themselves, and we can continue that in both columns. Oops, that should be a 0. Perfect, and now let's try this next column, which is going to be empty set, comma 1, symmetric difference with empty set, comma 0, which is just going to be 0, 1, because we have that the only intersection between them is the empty set, and the unique elements are 0 and 1. And then because it's abelian, we also get this off-diagonal symmetric element as well. Next, let's try 0, 1, symmetric difference with empty set, comma 0. And we see that the only elements that are shared are 0, so we're left with empty set, comma 1 are the elements that are unique to those two sets. And then that will reflect over, so this is empty set, comma 1. And finally, we'll try empty set 1, again 0, comma 1. And we see 1 is repeated, so we left with empty set, comma 0, and empty set, comma 0. So with that, we've written out the entire multiplication table of this set. So we've completed sections 1, 2, and questions 1, 2, and 3. So we are going to call that a day on the proof. With that, thank you.